Thin materials are some of the most challenging samples to test accurately for thermal properties. Unlike bulk materials, thin samples are flexible, fragile, and extremely sensitive to setup errors. Even small issues like surface roughness or inconsistent pressure can have an outsized impact on your results. Methods that work well for thick, rigid samples often fail when applied to thin films, producing results that might look repeatable but aren't actually representative. Many standard TPS thermal conductivity methods assume the sample is effectively infinite in all directions, but for thin films, that assumption doesn't hold. And because thin films contribute very little intrinsic thermal resistance, even a tiny interface gap or a slight bend in the film can introduce contact resistance that dominates the measurement. That's why thin sample testing requires specialized approaches, dedicated calculation models, and fixtures designed to keep the sample flat, smooth, and controlled throughout the test. In thin film testing, three factors often dominate uncertainty far more than they do in bulk testing. The first one is contact resistance. If the film doesn't make perfect contact with the sensor or adjacent layers, microscopic air gaps form. And air is a great insulator, so even a tiny gap can overwhelm the true thermal behavior of the film itself. The second factor is surface flatness. Thin materials can bend, curl, or even wrinkle easily. Even minor waviness prevents full contact and increases contact resistance. The third is pressure uniformity. Thin film testing relies on uniform contact across the entire sample surface. Uneven pressure creates localized gaps, distorts heat flow, and adds error. And here's the tricky part. If these issues aren't controlled, the data can still look consistent from the test, but remain inaccurate. So how do you improve accuracy and confidence when testing thin samples? It starts with preparation and setup discipline. One effective approach is layer stacking, commonly described in standards like ASTM D5470 and ASTM E1530. By stacking identical layers, you increase the total thermal resistance, making the measurement more sensitive to the film and less sensitive to noise. For this to work well, each layer must be centered, aligned, and laid perfectly flat, and thickness should be measured precisely using an accurate caliper. In some cases, contact agents like ethylene glycol can help reduce contact resistance by filling microscopic air gaps between the layers without significantly altering heat flow behavior. And usually a single drop is all you need. Consistent and adequate pressure is also essential. It helps ensure uniform contact across the full surface and reduces variability between measurements. The best way to achieve this is by using thin film specific setups, like rigid backing materials and a controlled applied weight designed to keep pressure stable and repeatable. For thin samples, method selection and fixtures often influence measurement quality more than the instrument itself. Because films are fragile and sample height is limited, bulk testing assumptions no longer apply. Both the experimental setup and the calculation model must be tailored to thin film behavior. For example, Thermtest patented 1D thermal resistance thin film module, or TRTF, uses a layered stacking approach with stainless steel backing pieces to support the sample, promote uniform pressure, and maintain stable contact. The calculation model works by stacking multiple identical film layers and measuring the thermal resistance as that stack grows. That resistance increases linearly, and the inverse of the slope gives you the film's effective thermal conductivity. This approach is especially powerful because contact resistance between the sample and the backing doesn't dominate the final conductivity result, which is often the biggest challenge when testing thin films. Here's the key takeaway. Accurate thin film sample testing depends far more on preparation, setup discipline, and method selection than on the instrument alone. Contact resistance, surface flatness, and pressure uniformity must be controlled, and bulk testing approaches shouldn't be applied blindly to thin films. With the right thin film method, the fixtures, and careful setup, you can generate reliable and meaningful thermal data, even for the most challenging thin films.